is that now we can consider spatial correlation, because spatial correlation is quite important, because you wouldn't imagine two sites sitting quite close to each other have very, very different sea level. Okay, so in this case, spatial. Oh, sorry. So here we are using a spatial temporal sea level model to include those spatial correlation. Okay, so let's move to our next example. So in this case, we are talking about kernel decomposition. So now we are using high gauge record in the same area, North America Atlantic coast, and you can see that the tie gauge gives you a really kind of noisy observation of sea level change during the last 100 to 150 years, and different tie gauge have different temporal coverage. Okay, so previously we used only one kernel for describing the whole sea level change variance, but now we are using multiple kernel. So why we are using multiple kernel here is that we can use specific kernel to describe different sea level change process, which have different spatial temporal scale. Okay, so usually, as you can find out that in Erica Ash's paper or some previous work by Robert Kopp or Jennifer Walker, which we will cover that later. But if we so a specific choice is kernel choices is that we use a spatially uniform kernel. So which is here. So you are only calculating the temporal covariance. You do not calculating the temporal covariance here. The reason for that, you want to describe a spatially uniform signal across all of the sites, which may corresponding to global mean sea level change, which is experienced equally in different sites. Okay, and now, but an important concept I want to cover here is that this spatially uniform kernel do not necessarily corresponding to global mean sea level change. It's just a conceptually straightforward way to convert spatially uniform kernel to global mean sea level. If you want to calculate global mean sea level, you'd better have sea level data across the world. Otherwise, you wouldn't call that a global kernel. Okay. So here, we better call that a regionally common kernel that was spatially uniform across our data region. Okay. And then we have a spatially and temporally long wavelength signal, just like GIA. It's kind of spatially and temporally moving really smooth and really large length scale. Okay, so you can set a kernel to describe this signal, and for something like highly tectonically active area, if we think about long-term tectonic movement, it's kind of temporally long wavelengths, but spatially short wavelengths. Okay, so if remember that we can set the wavelengths temporally and spatially by our hyperparameter, the length scale hyperparameter, if you remember. Okay, the next example of sea level change is ocean dynamic, which might be temporally short wavelength but spatially long wavelength in some location like US Atlantic coast. And then you can set. So here you can see here we use a temporally linear but spatially varying kernel here to describe the long-term process. But if we think about last 150 years, we can consider GIA, the vertical land motion caused by GIA, as a temporally linear process. And we can think about this spatially varying signal as a materified to kernel, so it's kind of varying spatially. And then we have a spatial and temporal nonlinear kernel. as we did before, which is used to decompose something like ocean dynamic and sediment protection, something like that. So because we are setting three different kernels, we can decompose these three different kernels' contribution to our final sea level prediction. Okay, I hope this makes sense to you. So let's now try to run that code in our collab. Okay, so here it's like, okay, we have multiple choices of kernel, and many of them do support temporally and spatially. So you can see that in our paper actually. So I send this PaleoSTEM paper to you, and there's a table showing you, okay, we have this kind of kernel choices, and you can see whether this kernel supports temporal data or not, right? Okay, we can find out that later. Okay, so let's load the data first. So now we have 3,800 data. So you can expect the calculation is much slower. So we wouldn't try to run that in collab because it might crash anytime. So we will try to run that in your local computer. So if you're not sure about how to run that, how to install PaleoSTEM in your local computer, please go to our GitHub page. You know, GitHub page. It's not really hard actually. You just run through five lines of code in your terminal, so you will be able to install PaleoSTEM in your local computer. Okay, and we do have more workshop tutorial page if you want to look at. We discuss a lot of things in better detail. Okay, now we load our data. Okay, so let's move on. So let's try. So here, I will demonstrate again how do you build kernels in PaleoSTEM. So now we have much more kernels now. So firstly, we set a global kernel, which is only a temporal kernel, right? If you remember, it's not global, it's regionally common kernel, which is only temporal kernel, okay? So we are setting, I call it global kernel because that was kind of easier for me to write. But you remember that was a regionally common kernel instead of a global kernel because we do not have global data here. So I set that as a Martin 32 kernel, and I set some variance, really non-informative variance, not really non-informative prior for these hyperparameters. And then I set a regionally linear kernel. Oh no, a temporally linear kernel and regionally variant kernel. Okay, so I said the temporally is a linear kernel, and for a linear kernel, I set a reference year, which is 2000. So what I mean by that is that for a temporal kernel, you kind of like doing a linear regression where you have, if you do something like that, if you think this red line as your mean prediction, you have a uncertainty like that, and there's a value where you have zero uncertainty, and this year is what we call reference year. This is quite handy because if you're doing sea level, you have some reference year, you kind of assume you know exactly where the sea level is, so you have zero uncertainty. So here we set the reference years to be 2000, so you can set any year you want to. Okay, then I set a Martin 52 kernel as our spatial kernel. I set the hyperparameter for spatial length scale, and I create this spatial temporal kernel by create a product between temporally linear and spatially variable kernel here, right? And then I set a regionally nonlinear kernel. But I set a Martin 32 kernel as a temporal kernel and Martin 52 kernel as a spatial kernel. and I set some hyperparameters for them, and I combine them as a product, right? And then lastly, I add a white noise kernel to describe some noise do not include in the data. Okay, so lastly, what I need to do is I combine all of them. You see, I combine global kernel with regional linear kernel, and I then add combined kernel with regional nonlinear kernel, and I add a combined kernel with white noise kernel. And then I create a Gaussian process model based on our X value, Y value, combined kernel, and noise. Okay, because I already set a Y noise value here, a Y noise kernel here, so I set noise to be 0. But if you do not set Y noise kernel here, if you do not use this command here, the model will automatically generate a Y noise kernel for you. Okay. So now, instead of optimizing it, I just use my previous optimization. I just load my previous optimization. It saves us a lot of time. Okay. And then I can start to generate predictions. Okay. So again, like I will encourage you to study resolution so it predicts a little bit faster. But for target data, if you cause the resolution, the prediction might look weird. So I will encourage you to kind of run this in your local desktop. But how does it look like? You know, it looks like that. It's kind of coarse, but how does that look like if we use 1 year resolution? Let me show you. Okay, look like that. Okay, look like that. So you have like some oscillation, but according to the data. Okay, and then you can not only predict in terms of temporally, you can predict that spatially, but again, due to the computational issue, we need to increase the spatial distance, so causative resolution. So let's change to the resolution to 5 degrees. You know, if you think about that, it's 5 degrees. It's really slow, so it's kind of annoying. So I will try to run this in my local desktop, so you will have a better idea of how does it. Okay, it's crashed. Sorry. So it's kind of so it's kind of like annoying. So in this case, we do need to. So please do not run 5 degrees. So it's kind of you can run maybe 10 degrees, something like that. So make it. So if we crash, I do need to terminate this kind of terminate this notebook and rerun everything again. So what's that? I will use my local desktop to demonstrate it for you. Okay. So this has become much bigger if you think about that. Okay. So if I run that, I run that in my local desktop. It's much bigger. Right. So what you see here is the sea level change between 1900 to 2023. This is our total sea level prediction, and this is our uncertainty estimation, right? And then the interesting you can do is kernel decomposition, right? Because we have a lot of kernel here. We have 3 kernel, a regional common kernel, a regional linear kernel, and a regional nonlinear kernel. And as I said before, you do need to find out those kernel in our Gaussian process kernel object, right? So here is our kernel object. You can see that the kernel, you can see that the kernel 1 is our white noise kernel, and the kernel 0 is the other kernel. Okay, you see kernel 0, and now the kernel 1 is our, you see the kernel 1 is our, so for every layer, it's only kernel 1 and kernel 0. Okay, so for this layer, you see that kernel 1 is our spatial temporal nonlinear kernel. You see here? So this is our spatial temporal nonlinear kernel. So that's why we input this object here. And then we try to find other kernel. So in this layer, the kernel 1 is our temporal linear kernel, right? That's why we put it here. And lastly, for the last layer, is our global kernel. I know it's kind of annoying, but it's kind of straightforward in this way. So in current kind of PaleoSTEHM, you do need to find out this kernel yourself. Okay, so if we find out that, you know, we put that in here, and we can now start to decompose our kernel. Okay, with the global kernel, so there's a specific function for you to do that. So for this, you need to predict the Gaussian process regression class, the prediction matrix, which give you kind of what time period or what spatial period you are trying to predict. Here we are trying to predict the single site, but from 1900 to 2023. Okay, so let's do it. Okay, so here you can see that we start to decompose the regional common signal, the temporal linear kernel, and the temporally nonlinear kernel. So you do see that there's a regionally common sea level rise, according to the TIH data, which might corresponding to global sea level rise, maybe due to the thermal expansion or glacier and ice melting, right? And you see that there's a sea level drop in this site. This is maybe due to the land uplift, due to GIA and this spatially temporally nonlinear. You do need some domain knowledge to explain this signal. This might due to ocean current changing or atmospheric dynamic changing, and very barotropic effects, something like that. So you do need to do that. But again, this signal do not have any physical meaning. It's just a statistical reconstruction. To explain those, you do need some domain physical knowledge, and it not always correspond to each other. Okay. And then we can do the decomposition as well in terms of spatially. Okay, so let's do that. I do decrease a bit about the spatial resolution to make it run quicker. Okay, so then you can start to see that here I just only plotted the location where I have low uncertainty, so I have a good confidence my reconstruction is accurate, right? So here you can see that, right, there's a sea level drop in the northern American area, so it's kind of due to GIA probably, it's kind of land uplift, so sea level is actually dropping quite a lot at this area. And here you see some sea level rise. Here maybe due to peripheral bulge subsidence or some global sea level rise signal in the East Coast. Okay. Again, I want to explain something else, is that you do see this kind of really red area here. This, but with really low uncertainty, really high uncertainty. You see this red blob here is that because the model the model need to maintain spatially continuous. So if you go up in this direction, it will go up continuously before it's dropping down. So usually we do not have too much interpretation about this kind of really high value here. But if you see a high value here, with slightly low uncertainty, you might think about that was something happening here. Here is like, it's a famous area where you have a lot of groundwater or oil extraction. So sea level rise here is much higher than others. So where you do not have data, you still see this kind of high value. We do not overinterpret this. Okay. So let's try to run that in notebook in the collab. So again, please. I hope you haven't run across your collab, but please decrease the spatial resolution, maybe 10, something like that. So make sure that your prediction is coarser enough that the Google Colab can handle. So the way to do that is you kind of change the spatial resolution to 10, maybe. So you can kind of handle it. Okay, so I will give you 5 minutes or maybe 5 minutes to play with it. Like if you don't want to play with it, you can have a rest. Okay, so we will be back at 10 past 10. Okay, so meanwhile, if you have any questions, let me know.